went around the, thank you very much for recording. So maybe I'll just repeat very briefly what was said and make sure that I'm recording too. Okay, very good. So we're talking about shortest paths and graphs. The edges can have different positive weights, in which case we'll have Dijkstra's algorithm. They can have negative weights, in which case we'll use Bellman-Ford. But then the question is, what is the shortest path? Because in this particular example, if you go from A to B, it's of length 1. If you go from A to B to C to A to B, it's of length 0. And if you keep going round and round, you can make the length of that path as small as possible. And so part of the problem here is detecting such possibilities, which are negative cycles, where if you keep going round and round, you can make the cost as low as you like. And so, and Bellman-Ford will actually detect that for us very inexpensively. The other case that comes up, which is simpler, is shortest paths in DAGs. Remember, a DAG is a directed acyclic graph. And since there are no cycles, by definition, we don't have to worry about negative cycles, and there's a much faster way to deal with that. So there are actually a bunch of other variants that are going to come up later in the semester, which I won't talk about today, but I'm just going to advertise it. So there's also the problem where you want not just the shortest path from one source vertex to everybody else, but you want all pairs shortest path. So from every source to every possible destination. And of course, you could run any of these algorithms n times, where n is the number of vertices, but that would take a long time. And so in fact, there's a cheaper algorithm that we'll talk about there in chapter 6. And yet another variation is called the traveling salesman problem. That's going to come up in chapter 8, where you want to find the shortest cycle. So you start and end at the same place, and you visit each vertex once. And as far as anybody knows, that takes an exponential amount of time, in contrast to the polynomial time algorithms we're talking about in this chapter. So we'll save those for later. So, and someone is asking, why is Dijkstra not suitable for negatively weight graphs? Well, we'll talk about that later. Just wait, you bet. So notation they're going to use throughout the lecture is the graph G will have a set of vertices V and edges E. And I'm going to use L, which is a function, takes an edge and gives you its length. And little d of S comma V is going to be the length of the shortest path. That's going to be my goal to compute that. So here's an example. And so let's just use our intuition to find the shortest path from A to everybody else. And so let me get a nice colored pen for this. So let's start at A and ask, what's the shortest path to everybody else? And the easiest thing is, what's the shortest path from A to A? Well, I think I know that answer. So, and the distance is going to be 0. So let me write it up there. And let me color in that vertex to indicate that I know that. So I figured out A. So the next step is, given that I know the shortest distance from A to A, what is the next vertex that I can add? So the goal here is going to be at each step of the algorithm, update the set K, which is the set of vertices to which we know the shortest path. So at the first step, the answer is A. So at the second step, let me just add this information back in. So we know the distance there is 0. We know the distance to A. So what is the next vertex that we could add to our set K? And let me just improve my writing there. Yes, so what is the next vertex that we could add? Well, from A, we can get to either B or C. C is closer, so our intuition is going to be that we're going to go to C, and the distance is going to be that length 2. Okay, so we're going to make this more formal later. And so let me now draw a little circle around this, which is going to indicate that we know, let me keep using red. So I've just enclosed the vertices that are in the set K at that point. Okay, so let's go on to the next step. And so we know the shortest distance to A, to C, and that distance is 2. And so the question is, what is the next vertex that we could add? Well, I know that I could get to B now by going from A to C to B, and its distance would be 2 plus 1. So let me just update that by putting a little 3 there. I know that I could get to E, and that distance would be 2 plus 5, so that would become a 7. And I know that I could get to D, and that distance would be 2 plus 4, or 6. So the question is, who should I add? Who's closest? And I hope your intuition is that B is the next one to add. So let me just do that. And so B is going to be the next closest one, and it's going to be a distance 3. And so I'm now going to grow my set K to include all of these vertices. And so let me go to the next step. And so I know A, B, C, and I know the distances are 0, 3, and 2. And so now I ask, who can I get to next? Well, I can get to D and E. What's the shortest distance to D? Well, I'm going to take the minimum of 4 plus 2. That's what it used to be, 6. But I can also go from A to B to D. And that's going to be 3 plus 2, or 5. And what about E? The old distance was 2 plus 5, or 7. And now it can be 3 plus 3, or 6. And so those are going to be the shortest distances. And so I will now add D as the closest. And so I'm going to add D to my set K. And this is what the set K is going to look like. And you can, and then I'm almost done. So the property that I care about here is that there are no vertices, and that I'm going to prove this, but this is the intuition. There are no vertices, outside K with shorter paths to them than those inside K. Okay, so now let us try to be a little bit more formal about this intuition and write down Dijkstra's algorithm. And so here's how it's going to work. It will take a graph and a source vertex for starters. And just to remind you, a graph has a set of vertices and a set of edges. And I know the distance to the source. So let me just initialize this array dist, which is going to contain all the distances, to be 0. And I'll initialize everybody else to be equal to infinity, because I don't know yet. So for all vertices that are not equal to S, I'll set the distance to infinity. Now, when I get started, my set K of all the vertices, whose shortest distances I know, is going to be empty, and I'm going to continuously update it. So these are the vertices to which I know the shortest paths. And so as long as I haven't visited everybody, so while the set of vertices for which I know the shortest paths does not equal everyone, I'm going to pick the U in the set of vertices that aren't yet in K. So that notation is v minus k with the smallest distance. And I'll add it to k. And now, once I've added that, I have to update everybody else, all the other distances. So, and what do I know? I know I'm going to update that based on all the outgoing edges from U to all other possible vertices V. And I'm going to update the distance to V to be the minimum of what it was before. Because if I only find a longer path, that's not interesting. So it's going to be the minimum of the distance to V and the new possible path through this new edge, which is the distance to U plus the length of U comma V. Okay, and we're going to call this function update later. So let me just note that. Okay, so that's what captures the intuition from my previous slide. Okay, so now comes the proof of correctness. And so this is going to be some careful reasoning, and it's going to be by induction on the algorithm. And so let me just recall the notation, which was that what I want to compute is d of s comma v, and that's the length of the shortest path from s to v. And let me say of a shortest path, because shortest paths aren't necessarily unique. Okay, so here is the claim that I want to prove. At any time, for all vertices that I've chosen and put in the set K, the value in this array that I've computed is the true distance, true length of the shortest path from S to V. Okay, so that's what I need to prove. And I'm going to do it by induction, one step at a time. And so the base case is pretty simple. Because I'm starting with K is the null set. And so obviously all vertices in there, I know everything about them because there aren't any. But what's the first step? It's going to be to, so remember, what are all the distances? Let me go back. I have set the distance to the source to be 0, and all the other distances are infinity. I have to pick the minimum, and the source wins. So after the first step, K is just the source. And it's obvious that the distance from the source to itself is 0, which indeed equals dist of S. So that's the base, sort of the real base case. So now let's do the induction step. And so let me let V be the vertex with the smallest distance. Which is what I'm going to be selecting. And the claim is that, as I said, the distance to that vertex is going to be the desired length of the shortest path. So let me, to argue that, let me give myself some more space. Let me let this be a shortest path. From the source to the vertex, V. And V is not in K. and let this be a shortest path. Now I want to break this path into two parts, and the first part is going to be up to vertex A, and the second part is going to be vertex B. And the idea is that all of these are in K. S through A, that part of it's all in K. And B is the first one not in K on the shortest path. Okay, so I'm going to use the fact that every prefix of a shortest path is a shortest path. So in other words, I'm going to use the fact that this partial path at the beginning here, just from S going up to A, is also a shortest path. So why is that? So since the whole thing is a shortest path from S to V, if there were a shorter way to get from S to A, I would take that, and then I'd go from A to V, and I'd get a shorter path from S to V, contradicting the fact that I have a shortest path from S to V. So that means that every prefix is a shortest path. Okay, so so now let me try to prove this, and there are going to be two cases. And this is the interesting case if B equals V, and the other case, of course, is B does not equal V. So in that case, if B equals V, then that implies trivially that dist of V, which is the number in the algorithm, is dist of B. And that's, since they're the same. So let me just write down all this logic. So since B equals V. And so now, what else can I claim? What is the dist of B? Well, the way the algorithm computes that is that it takes the min of the value it had before and the dist of A plus the length of the path from A to B. And that is the inner loop of the algorithm. That's a line of code that's executed. So I know that's always true. And so now, what is the dist of A? So I claim that's actually equal to the length of the shortest path from S to A. And why is that? And that's because A is inside of K. And so that's true by induction. Right? I'm assuming that this is true for all the vertices I've added so far, and I want to prove it for the next vertex. So now, what is this sum? It's the length of the shortest path from S to A plus the length of the path from A to B. And that's a prefix of the, so this is the length of the shortest path from S to B. And that's based on the fact that the path from S to B is a prefix of a shortest path, so it's a shortest path. And since B equals V, I get that's the distance from S to V, which is what I wanted. So, so I have proven that the dist of V by induction is equal to the length of the shortest path. So that is the most important part of the algorithm. Are there any questions? Let me look at the chat. It looks like the GSIs have things under the control for the moment.
Professor?
Yes.
One small potential correction on the third to last line. Should that be or the fourth rather, should that be a B rather than a D?
That is just, yes, my bad handwriting. That's a B, absolutely.
Gotcha. And then I think another thing that some people are asking about is what a quote like prefix of a path is, of the shortest path is.
Okay, so good question. So here we have a shortest path up here, and a prefix is just, the first, take a leading subset of it. So, it goes from S to, let's say U1, U2, U3, U4, and to A. And so that whole path is called a prefix of the path from S to V. Is that okay?
I think that makes sense.
Okay. So that's the case if B equals V. And obviously, I should have left myself some more space. So here's the other case. What if B does not equal V? That is a contradiction. That would imply that the distance to B is less than the distance to V, but because this is the shortest path. But I was assuming that V was the one I'm choosing next. So this is a contradiction. The algorithm choosing V next. Okay, so that is the end of the proof of correctness. Are there any questions about that? Okay, so now let me go back to Dijkstra's algorithm, which I've written here. And what I'd like to do is update it, and so that we can, I'm going to put in some more details so we can understand its running time. And so I'm going to, instead of using a set K, I'm going to use its complement. So I'm not going to do this one. I'm not going to use K as a null set. I'm going to use the set U equals the entire set V. And so more generally, what I'm going to use is that U is the complement of V. So it's V minus K. And I'm going to use U throughout the rest of the algorithm. So instead of asking, while K does not equal V, I'm going to ask, while U is not the null set. That's the same thing. And then instead of picking U in V minus K, I'm going to pick little u in capital U, same idea. And then instead of adding U, little u to capital K, I'm going to remove little u from big U. So this is just notation. I haven't really changed anything yet. So what I need to do now is just look at this. I need to pick this line, the vertex little u from a set big U with the smallest distance. And then I also need to do this updating. And so the question is, what is the data structure that I'm going to use for all of that? So let me write this down. For picking the smallest. And also updating it. So the question is, do you remember from 61B what a good data structure might be for that? It's called a priority queue. And let me change colors here. So I'm going to update the algorithm again. I'm going to use something called a priority queue. Okay, so let's go back and use that data structure to modify this. So here at the beginning, when I'm initializing stuff, what I'm going to do is initialize the priority queue to contain everything, all the vertices that I need, and the keys, because the priority queue is going to be sorting on some keys, are going to be this function called dist. So initially, dist of s is 0 and dist of all the others is infinity. So this line, if u is not empty, is going to change to if the queue is not empty. And then what does it mean to pick u with the smallest distance? That is going to be in priority queue lingo. It's going to be called delete min. That picks the vertex off of the queue with the smallest key, which means the smallest distance. So now what do I do down here after I update, after I recompute the distance? I'm still going to use that particular function, but what I need to do, and let me insert the line of code over here, is call a function called decrease key. And I'm going to pass in q, the vertex whose key I want to decrease, and this value, which I just computed in the previous line, dist to v. And so that is what the actual code is going to look like, assuming I have a priority queue implementation. Let's see, and there's a question. Pick u, yes. So there's the question. And let me go back and use the right colored ink. So this should be u, a member of u. Yes, thank you. Yes, that's what that should be. So now the question is, how do you implement a priority queue? And so let me just review a little bit from 61B. We're not going to go into the details. And the typical way you do this is with something called a binary heap. And which is basically a tree. And all of these functions that we need to implement, called delete min and decrease key, and insert, if you recall, all of those cost log of the number of vertices time. So that is the algorithm that we're going to use. Now, that's not the only one that people have invented for this problem. I'll just put ... There are a lot of other fancier algorithms, but priority queue is good enough for most purposes. A binary heap is good enough for most purposes. But let me just mention, there's something called a Fibonacci heap, which is more complicated, but even a little bit cheaper. Okay, so that's going to be my building block. I have to know how much each basic operation costs, which is going to be order log v. And now I have to ask, how often is each one executed? So let me go back to black ink. And so what I need to do is count the number of operations. And then multiply them by the cost per operation. So we're obviously going to only make the queue once. And there are two ways you could imagine doing that. Either by doing v inserts, and that implies the cost is going to be v log v. Or there are fancier methods, which I won't go into because which are just linear. Order v, the size of v. Let me fix that. Order the size of v, because this term is going to be small compared to the others, so it doesn't matter too much. So the next operation is delete min. And so how often do we do that? Let's go back and look at the code. How often are we going to do delete min over here at most once per vertex, right? Assuming we can reach all the vertices. So this is going to be once per vertex. And so that's going to be a total of v times. And that'll get multiplied by log v in a moment when I do the cost per operation. And then how often do I do decrease key? That's going to be once per edge, because I'm going to look at each edge at most once. I may not look at some edges if I've already, taken the vertex, its vertex out, and put it in the shortest path. But it's at most certainly the number of edges. So what's the overall time? It's going to be order of the number of delete mins plus the number of decrease keys times the cost of doing any of those basic operations, which is log v. And that's using the binary heap. And you can actually get it down to be cheaper if you're using Fibonacci. And I'll just tell you what it is without going into the details. So it gets rid of the E log V term. It just replaces it with the size of E. And so this can be useful if the number of edges is much, much larger than the number of vertices. So if you have a nearly dense graph. If everybody's connected to everybody or something like that. So just to let you know, there are even more complicated algorithms, which we're not going to talk about. And they get the cost all the way down to nearly linear. Not only are they more complicated, but those hidden constants are worse. So a binary tree is good enough for most purposes. So I wasn't going to go into any more details about data structures in the hopes that you can all review your 61B material if you like. So that is the end of Dijkstra and how to deal with shortest paths when all the edge lengths are positive. Are there any questions? Looks like things are under control. Okay, so let's move on. Why does it break for negative? Yes, we're about to get there. Yes, the next topic is shortest paths with positive or negative edges. So let me give an example of what might go wrong if you try to use Dijkstra. So let me have a little graph that looks like this. And so this edge is going to have lengths, let's say 2, 100, minus 99. And then there's a much more complicated graph sticking out of C. So what would Dijkstra do in this case? It would look at all the outgoing edges from A to B and to C, and it would pick C. So let me just color that in. It would start at A and it would pick C. Now let's suppose that all the other edges are much, much shorter. Say they're of length 1. So Dijkstra is going to continue exploring all of this space. So it's going to do all its work and figure out everything in there. And then eventually it's going to look at the edge from A to B and B to C and say, oops, there's a shorter path from A to C of length 1. And that means that all this other stuff that I've done up here is wrong. And so you can't make that you can't look at things in just sorted order, because you can do an awful lot of work and it'll be useless. So the other example that where something can go wrong, and we saw this before, is when you have negative cycles. So let me draw this simple graph again. And let me label the edge lengths 1, 1, -4, -2, and 3. So what's the shortest path? What is the distance here? The distance from A to C. Well, if I just go ABC, I'll get a distance of 2. But then I realized I could go to A, B, D, E, C. And so in other words, I will take this path, A, B, D, E, B, C. And what's the distance there? Let me sum up all the edges. And the answer is -3. So let me try that again. Let me try this particular path. So I go from A to B to D to E to B, and then around the circle again to D to E to B, and then to C. What is the length of that path? It's going to be, oops, that wasn't -3. Let me get that right. The first one I did was -1. And the one I just showed you was -4. Okay. And dot, 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 if I keep going around that negative cycle over and over again, so this is what's called a negative cycle, I can make the path as small as I want. And so it doesn't even make sense to talk about shortest paths in this case. So we wanted to detect when that negative cycle exists. It's certainly an interesting phenomenon. So let's talk about what properties we have of the update function. So we're still going to use that update function that we had before, but we're going to use it in a different way than Dijkstra did. So let's just remember what update did. So what did that do? It set the distance to V to be the min of the distance to V and the distance to U plus the length of the edge from U to V. Okay, so that's update. So, and we call that if UV is an edge. Okay, so that was the inner loop of Dijkstra. So what properties does this have, even potentially if edge lengths are negative? So let me just say first that update is always what I'll call safe. So that means that whenever I execute it, I can't make the distance to V smaller than the true distance, right? Because this formula update is always considering one particular path. And so it's always going to be bounded below by the length of the true path, D. That's the length of the true shortest path from S to V. So what does that mean? That means that extra updates are okay. I can do lots and lots of updates, and I'll never get an answer that's too small. So here is the other property. If the shortest path from S to V is the following. So S, and it moves along for a while. And then the next to last vertex in the path is U, and then the final vertex is V. And I know the distance, and I've gotten the distance to U right. So it's equal to the length of the shortest path. and then I run update, then the distance to V will be correct. Because I'm just taking the distance from S to U and going one more, and we have that property that if you have a shortest path, then all prefixes are shortest paths. So that tells us that we can do updating over and over again. And as long as I update, for example, all these vertices in order, so if I update that using that edge first, let me use a different color. So if I do this one first, and then I update that edge, and then that edge, dot, 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 and I do that one in that order, then I will get the right answer at the end. Okay, so this is the idea in Bellman-Ford. So let's suppose that we have a shortest path from S to V, and it looks like this. So S goes to U1, to U2, to U3, dot, 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 up to U sub T, and then to V. Suppose that's the shortest path. Then let's suppose I, at some point in a sequence of updates, do update S comma U1. By that property that I just told you on the last slide, then the distance from U to U1 will be the true shortest length of the shortest path from S to U1. Now, if I then update using the second edge, so that's the edge from U1 to U2, that will imply that the distance to U2 is also equal to the length of the shortest path from S to U2. And this is just going to continue. Let me update the next edge. So from U2 to U3, that will imply that dist of U3 is also the length of the shortest path. Dot, dot, dot. And then finally, if I update the last edge, UT to V, that will imply that dist to V is what I want, which is the length of the shortest path from S to V. Okay, so that's if I do all of those updates in that order. So, but how would I know to do that, right? I don't know what the shortest path is. So here's the idea. I'm going to do a very long sequence of updates. But I'm going to guarantee that all of these updates appear in this list somewhere in that order. So this is going to be a long sequence of updates, but they're going to include every possible listing. And so if I do that, then at the end of this point, I will have dist of V will be correct. This is using the property that doing extra updates is safe that I had in the last slide. I can do as extra updates, no problem. As long as I do these updates in the right order, then I will get the right answer at the end. So Bellman-Ford is going to do enough updates so that all of these things will always appear. So how are we going to do that? So let me write down the algorithm, which is just two loops. It's very, very simple. For I equals 1 to the number of vertices minus 1. And then for all edges, run update. So look at the outermost loop. So when I equals 1, I'm going to do all the edges. So I will succeed when I equals 1 of doing that one, that because I'm going to do update every edge. So that'll be in there. When I equals 2, I'll for certainly do that one. When I equals 3, I'll certainly do that one. And how long can this shortest path be? How long can this be? So how long can a shortest path be? Well, it can't ever be longer than the number of vertices minus 1, right? Because I'm not going to have any cycles in this. And if I had v vertices there, I would, 2 of them would have to be the same. And so this will certainly occur before I get to that point. Okay. So, so let me just, say what I did, repeat what I said there, is if I have no negative cycles, so that's going to mean that all shortest paths have at most v minus 1 vertices in them. Because otherwise, if I had v vertices, then it would have to come around and have a cycle in it, and that could only make it longer. So that means that, as I said, all updates appear in the desired order. And by desired order, I meant this order here that I showed you before. And so that means all the disks are correct. So what is the running time? This is very simple because it's just 2 nested loops. It's going to be the number of outer loops, which is v minus 1, times the number of inner loops, which is just over all the vertices, times the cost of updating, which is just a constant, which is going to be then order of number of vertices times the number of edges, which is certainly not linear. It's bigger than we had before. In fact, in the worst case, it could be the number of vertices cubed if I had, a dense graph where the number of edges was close to the number of vertices squared. So that is Bellman-Ford, and it works assuming there are no non-negative edges. And in case you're interested, and I hope you are, I see a question in chat. What if there are negative edges? Then, negative cycles, then what happens to Bellman-Ford? Well, the good news is that we're going to use Bellman-Ford to detect that. And so we'll do that very shortly. So now let me talk about shortest paths in DAGs. And so this is, remember, a DAG is a directed acyclic graph. So by definition, it has no cycles. And so obviously it has no negative cycles. So a whole bunch of problems go away. So we can have positive edges lengths, negative edge lengths, and so it's fine. So positive and negative edge lengths, okay. So the nice thing about DAGs, it's going to be very cheap to figure out the order that we would do in Bellman-Ford and actually only do every vertex once. And so we're going to use an idea that we had before, which is called topological sorting. Starting with the source vertex, which you're given. So who remembers what that means? That means that I'm going to order all the vertices in some order. And all the edges go from left to right. So they all look something like this. etc. And how do we do that? That was a simple, depth first search. So we know the cost of that. It's very cheap. So now, what does that mean if all the edges go from left to right? What can a shortest path looks like? So we'll start at S, and that'll go to, say, U sub I1, and then we'll have an edge from U sub I1 to U sub I2, and U sub I2 to U sub I3, and so forth. And what do I know about that? That all of these are going to appear in sorted order, because all the edges go from left to right. So what does that tell us about the Bellman-Ford trig? It tells us that updating all the edges, UI to UK, in order of increasing I, works. Every shortest path will have all its edges updated in the right order exactly once. And so in other words, this order here that I had will appear, for every possible shortest path, because all the edges are going to be done in that order. So what does it cost? That's going to be topological sort, which is depth first search, which is going to be order the number of edges. And then we order the vertices by decreasing post number, plus updating in order. And so the whole cost is going to be order of the number of vertices plus the number of edges. So it's going to be linear. Can't do better than that. Okay. Very good. So this is shortest path from DAGs. And okay, I don't see any pending questions in chat, but so let's move on now to the last topic, which is detecting negative cycles. And so we're just going to use Bellman-Ford for that, and we're going to do it as follows. So it assumed no negative cycles when I did the proof. And so that meant that, in particular, that all shortest paths, each vertex can appear at most once. And so that means they can have at most number of vertices minus one vertices in them. Okay. So now here's the theorem that we're going to prove. And that is, and we're going to use it to modify Bellman-Ford to construct an algorithm. So we have no negative cycles in the graph if and only if running Bellman-Ford for one more iteration and what do I mean by that? That means update all the edges one more time. doesn't change any edge lengths. Doesn't change any values of dist for any vertex. Okay, and so what does that mean for detection? That means that we're going to run Bellman-Ford v times, the outermost loop v times, instead of v minus 1. And then we will signal a negative cycle if any dist changes. Okay, so that's a very simple thing. So here's the proof. So this is if and only if. So the implication goes in both directions. So I actually have two proofs to do. And so here's the easy direction. So what if I have no negative cycles? Let's assume that. So that implies that all shortest paths, as I said above, have at most v minus 1 vertices in them. And so updating one more time is safe and nothing changes. Okay, the other direction is the interesting one. So let's suppose now that we run Bellman-Ford, and let me give myself some more room here, and run Bellman-Ford, and no distance changes. So what I want to do is prove that there are no negative cycles. So let me build a cycle and see what happens. And it's a cycle of length t. And so what I want to do is add up the weights along all of those edges and show that they can't be negative. Okay, so let us just ask ourselves, what happens if I run Bellman-Ford and nothing changes? Well, one thing that I know from that is that the distance to A1 is going to be less than or equal to the distance to AT plus the length of the edge from AT to A1. So this is, remember, in the inner loop, when I run update, I ask whether the distance to A1 is less than that, because there's an edge from AT to A1, and it has to be less than that, because otherwise dist of A would change. Otherwise, dist of A1 would change. Let me do the same thing for the next edge. So I also can conclude that dist of A2 is less than or equal to the dist of A1 plus the length of the edge from A1 to A2 for the exact same reason. And so let me just do ... and write down every formula for every edge there. And the last one is going to be that the dist to A sub t is going to be less than or equal to the dist of A sub t minus 1 plus the length of the edge from A sub t minus 1 to A sub t. So I have all of these inequalities. Let me just add them up. I'm going to take all these inequalities and add them up. So what do I get? And since they're all inequalities, I'll get another inequality. So what happens when I add up all the inequalities on the left of this sign? I'm just going to get the sum from j equals 1 to t of all the distances. That's the sum here. So what happens when I add up all of these other distances? Well, I'm still adding up the dist of A1, A2, A3. I'm just adding them up in a different order, but I'm going to get the same sum. So those two terms are identical, and I'm going to cancel them out in a moment. But now, what do I get here? I'm going to get the sum of all the edges in the cycle. So if I do the cancellation, I get 0 is less than or equal to the sum of all the edges in the cycle of their lengths. And that obviously means it's no negative cycle, because it's the sum is greater than or equal to 0 as desired. Okay, so that is why Bellman-Ford is correct. And that brings us to the end of all the topics I wanted to talk about today. I think I may have gone through them a little faster than I thought, so I'm very happy to stick around and ask questions.